Okay, hello everyone. So I'm going to present, pause this one, the result from the work that we've done during the Annex 68, so during the first subtask of this Annex. And we'll draw the whole methodology we used. So we gathered some data on pollution levels, on exposure limit values to have a list of pollutants of interest for the annex. And we also define some indices to evaluate the indoor air quality. And the second part, which is the end of this presentation, I will want to share the limitation of this work and what should be improved when designing indoor air quality metrics. So the first part is about subtask 1. The subtask 1 lasts just 1 year. It was 1 year of work at the beginning of the project. And we wanted to answer 4 different questions. Firstly, we wanted to have a look at the pollution level in low energy buildings, because the focus was low energy buildings in this annex. And we wanted to compare it to older buildings. The second question was to answer the question, what are the target pollutants where we should take care in this annex for low energy buildings, residential buildings, how to quantify the indoor air quality, so it's the question of the metrics, and also the last one was to account the energy consumption related to indoor air quality. So as I said before, we gathered a lot of data actually to have a look at the pollution levels in residential buildings. We had a lot of data from older buildings, non-low, like we call it non-low energy buildings, older building and low energy buildings. From all around the world, you have all the different reference on this slide. And what we are able to draw is an illustration, a picture of the concentration levels for different pollutants in yellow orange for the older building, in blue for the newest one, low energy buildings. And on the whole, you can see that there's a slight reduction of the pollution level for almost all the different pollutants, with some exception with alpha pinene, for example, or xanel. There's a slight increase, which can be caused by the fact that a lot of new low energy buildings were made of wood, construction wood, that tends to emit more of this compound in the air. So with that, we had what we were interested in is to have the blue level here for the different pollutants, and we wanted to sort the importance of these pollutants. So we needed to have a concentration preference to deal with, and it's when you are interested in that, it's the whole world of the exposure limit values that comes from epidemiological study or animal experiments for them. And they are established nationally and worldwide by health agencies, and they're different from country to country, actually, because of feasibility of the application of this kind of limits. The other thing to know, I won't go through the whole figures here, but the other thing to know is there's mainly two kind of exposure limit values. The one for the long-term effect, which potentially imply a chronic risk for health for people, and short-term effect. Long-term is the whole life, 1 year, something like that. A short term can be hours to 1 day, almost. And in this annex, we were interested in one kind of all of the indoor environments, which is the green one here. But sometimes for the short term, we needed to have data. For the short term, we had to look at the work environment also for this data. So our methodology to define target pollutants was to use the data of the pollutant concentration levels I showed you before, to use this exposure limit value, this database that we had, and we chose to take the lowest exposure limit value for each pollutant, considering separately the long-term effect and the short-term effect. And we made a simple ratio, actually, of this concentration by the long-term effect. And to be more conservative, actually, we use as a key rule ratio higher than 0.1, sorry, not just 1, to decide that there's the pollutant with ratio higher than 0.1 was of interest for our problematics. So doing that for long-term and short-term effect, we were able to classify the different pollutant in blue for long-term, in orange for short-term. And we were able to draw these two tables here, again with the same color code. It's about 16 pollutant list. In fact, with this methodology, we were able to do only 14 pollutant. We added acrolein because we know that there's some problem in residential building, in all the building with acrolein, but we didn't have any data for new ones. So we added it, even if we didn't have a number of methodology. And we added also the mold because of the lack of data on new buildings also, just to be sure to include every non-pollutants in our problem. So with this list, we needed to calculate some metrics. The idea was to have only one metric at the final of the project, but for each pollutant, we needed to define some indices, and then to have only one index at the end, we needed to define a function to aggregate the different sub-indices in the calculation. So also we made a literature review about existing metrics in the past studies. So for the first terms, what we used, actually, we used the ratio we used to define the target pollutants. So it's the ratio of the concentration over the ELV value. But others offer use a different way of doing that, defining, for example, a scale to compare the different pollutant, to calculate an index for each pollutant according to a scale from 0 to 100 for this one, but most of the time it's 0 to 10 or 0 to 1 also. But using this approach, you need to have a definition of breakpoints that leads to additional arbitrary choices, and we wanted to avoid at most of possible the arbitrary choices. So we just use this simple ratio here in our study in Annex 68. To make the aggregation, you find plenty of different forms to aggregate the sub-indices, from direct summation or weighted average or root mean square, or even a simpler one like max operator or mean operator, the complementary index that we can find. And I will just take 1 minute or two to put into relief some limitation of aggregation that Sharma and Bhattacharya showed. And I will take just a simple example considering two pollutants, so two sub-indices here, defined as the ratio I showed before. So if it's lower than 1, there's no risk. If it's higher than 1, there's a risk for health for this pollutant. And the aggregation, we wanted to find a function. And with the same quality, the same rule here for the aggregation. If it's lower than 1, for example, I could have taken other value here, 2 or 0.5. Any value will suit for the example, but 1 is more convenient here for this example. So we can think of direct submersion, for example. And if we do that with this example here, what I show with some numbers here, but any couple of sub-indices lying in the red zone here will do the same as a conclusion. Is that there's no risk if you consider pollutant 1, there's no risk for pollutant 2. But if you aggregate making the direct submersion with this rule here, you will detect a risk using this definition. So that's what they call the ambiguity, or I call it false alarm in this case. So we want to avoid this kind of thing when you're defining the function here for the aggregation. So a simple modification could have been to take the average of the two. And this way, you don't have any problem in the first red zone, but some new red zone appear. And then here we have the opposite reaction for the aggregation. For pollutant 1, there's no risk. For pollutant 2, there's a risk higher than 1. And the aggregated index shows no risk. So here it's what they call eclipsing, which is another problem. We don't see a problem for sub-indices. And this region always exists when you use any mathematical relation here, except one. There's one that works every time, that unambiguous and non-eclipsing. It's the max operator or min operator, depending on how you define your sub-indices. But max or min is the right choice to do. So we used here in this work the maximum of the sub-indices to calculate the aggregated index. We use also another approach. I won't tell a lot about this because the presentation of Benjamin will be on that. So it's the DALY approach, the disability adjusted life years approach. Just to say one word about that, one DALY can be thought as one lost year of healthy life. It's like because of disease induced by the exposure to a particular pollutant. It's the equation at the end here. We got the exposure here for a disease. You can sum up the disease, this function, which gave you a DALY, a number of DALYs. And so you do that for every pollutant of interest, and you can make a summation at the end amongst all the pollutants. And so we'll let Benjamin talk about that later. So we ended up with this representation of indoor air quality and energy consumption for the annex, for the residential buildings. Actually, we ended up with 3 indoor air quality index. The 2 first, the blue and the green one, are for long-term effect, and the red one is for short-term effect. And the energy, we connected it only to the energy consumption, to connected with indoor air quality. That means we connected with ventilation, filtration, and cleaning device if they are present. Okay, so some limitation now of our works. First main limitation was the number of data available in terms of level of pollutant in low energy buildings, because they were new. There was not a lot of study and measurement in these new buildings. There was some problem about the quality of the data. Most of the time we had only aggregated pollutant concentration over building several buildings, with no detail really for each buildings to be able to try to classify it with lateral ventilation, mechanical ventilation, this kind of thing, for example, or airflow rate. That was another problem. Another problem was that available concentration data were obtained with usually 1 week duration, sometimes 2 weeks, even less, which is kind of okay for long-term exposure because we know that the weeks repeat during the year. But normally we use at least two periods, one during the winter, during the heated period, and one during the summer, where there's more ventilation but higher temperature, to really have a good overview of long-term exposure to the pollutants. And for short-term exposure, it's less precise because we need actually continuous measurement, at least to have some data, average data connected to the ELV duration period, which is 1 hour, 2 to 3 hours, or 24 hours, depending on the pollutant. It can be done for particles and some compounds like CO2, for example, but for VOCs, most of the time we had only 1 year yearly average. So we took the maximum of that to try to calculate the risk or to define our target pollutant. But there's a clear underestimation of the maximal value here using our calculation. The time of measurement, of course, these buildings, these low energy buildings, were brand new most of the time, and the measurements were done right after the end of the construction. So it's clear that the emission in this case were higher than that there would be during the rest of the year. So here we have also another estimation here of probably of exposure. Regarding the ELVs, exposure limit values, there are different values from country to country, and also they change with time with new advances of the research or the new findings about some pollutants. So here to counteract this problem, we took the lowest here. Was it the best thing to do? Maybe taking an average will be better. I don't know. We took the most conservative one actually, and the ELVs just don't take into account the cocktail effect. So this was that's why we took 0.1 instead of 1 for the ratio to avoid also this kind of thing that we don't take into account here. I won't go back to the DALY approach. The real good thing about DALY approach, it's you calculate the effect of the different pollutant on the same unit. So you can add it directly with this unit. You can monetize that. It has been done at country level for USA, France, England, I think. So you can, in a way, have a potential to integrate it to an economical assessment with energy consumption. But at the time of our study, there was some uncertainty on the number of daily losses estimated for different pollutants. In particular, we see that particles, PM, is very high in terms of daily compared to VOCs. There's a factor of 10 almost between the two regarding the exposure in the buildings. And that's it. So time running. So I'm going to the main conclusion. So we define 16 target pollutants, but probably we can reduce this pollutant to 6 or 7 main pollutants. And we show that during SUBTASK 4 of the Annex. And the quality of a good index for us is that it should include all the most important pollutants for the considered environment, indoor environment. It won't be the same for residential building than for office building, for example, or school. It should account for long-term and short-term exposure, avoid ambiguity and eclipsing, and also if it can be expressed on a scale compatible with energy consumption. It will be great to include that in the balance. So you will find a report and also a spreadsheet to calculate directly the different indices of Annex 68 on our webpage. And with that, it's 20 minutes here. I will pass the ball to Benjamin. We discuss about the DALY approach here.